Hi, and welcome back to MSc. In today's lesson, we're going to be looking at Le Chatelier's principle, specifically looking at the effects of changes in pressure on the equilibrium. So here we have our generic equation of A plus 3 moles of B going to C and 2 moles of D, and this is an equilibrium reaction. Notice here we've included the state conditions, and these are all in the gas state. And that's going to be important as we move through this today. We also have the equation here below for the equilibrium constant. And as we've seen before, this is the concentration of the products raised to their coefficients over the concentration of the reactants raised to their coefficients. So when we're looking at the effects of pressure on an equilibrium, we have to understand first and foremost that this will only affect the gas species. So gaseous moles will be affected, liquid and solid species will not. So in a few moments we'll look at some examples that won't have all gas species. Right now I have the equilibrium position lying here to the right, indicating that we have more product than we do reactant at equilibrium. Again, equilibrium involves equal rates forward and backwards, not equal concentrations. So let's look at this scenario here. If we were to have a pressure, and let's assume that we're going to have this pressure increase. So an increase in pressure is going to favor the side of the reaction here with less moles of gas. If we look at this side here we have 4 gas moles, and on the other side we have just 3 gas moles. So the increase in pressure is very much like increasing a concentration for the gas. If we know back to PV equals nRT, we know that an increase of pressure will actually involve a decrease in the volume if moles and temperature are held constant. And here's our concentration formula. So we understand that a decrease in volume will result from an increase in pressure, and that's going to result in an increase in concentration because we're dividing by a smaller value. And so really what we're thinking about is for gases, it's kind of like an increase in concentration when you increase the pressure, but we have to look at which side has more. So there's more moles on the left side here, and so we know that when we increase concentration, that it's going to shift away and try to remove that. So it's actually going to shift this reaction to the right, and this will shift to this side. So you don't have to go through the concentration kind of mentally in your head every time. You can just remember that increase in pressure favors the side with the less number of gas moles. So it's going to shift in this direction, the equilibrium will. Okay, and so I would say, okay, well, this, I'd probably end up with more concentration. It's going to shift further this way. But again, what's important here is also that Kc is unchanged. It does not change, just like it didn't change for changes in concentration. So this is unchanged. Again, the only thing that will change Kc is temperature. So watch for that in a later video. So at the new equilibrium, we will have a newly established rate forward and backwards. Those forward and backward rates are probably going to be a little faster than they were originally because the increased pressure makes for an increased concentration, more moles in a smaller area, or smaller volume rather, and that's going to drive up the rate of reaction. But we'll still have a forward and backwards that will be equal. Kc will be unchanged. We'll have new concentrations that will be reestablished that will make sure that Kc does not get changed. If we repeat this example, now with pressure being dropped, so a decrease in pressure, well, that's going to favor the side with more moles of gas. You can think about it again in terms of that concentration. Or you can think about it in terms of it's trying to decrease the pressure, so you want more gas molecules there to try to undo that. So this will shift in this direction, it will shift to the left. And so we say that the equilibrium will shift left. And so we'd actually see this point of equilibrium, wherever it was originally established, shift towards the left. Doesn't mean it's going to shift all the way over. How much it shifts will depend on where it was originally in the species involved and how many gas moles and all that other stuff as well. Again, new rate of reaction will be established, probably lower rates forward and backwards, but they'll be equal. Lower rates because reduced pressure, less concentration of the gas, and so probably a lower rate. We'll have new equilibrium concentrations that will be established, all to keep Kc unchanged. If we then look at an example here where we have a solid here, so draw your attention to this solid state. It doesn't have to be a solid, it could have been a liquid as well, but the idea is that it's not a gas state. So on the left-hand side now, I see just 1 mole of gas, and then on the right, I now see 3 moles of a gas substance. So let's look at some scenarios here to see what's going on. If I look at the pressure, and let's increase the pressure to start. So we'll say, okay, we're going to drive that pressure up. An increase in pressure is going to favor the side with the least number of moles of gas. So now we have this side has the least number. It only has 1 mole. The other side has 3 moles. So this is going to shift the equilibrium in this direction. And so we'd see that this equilibrium would shift over to this, in this direction. Again, Kc is unchanged. We establish new rates, forward and backwards being equal, and we'd have new equilibrium concentrations. But this is different than the other scenario that we looked at where pressure increased and it shifted to the right. Here it does not do that because this one had 3 moles of gas versus 4 moles. In our current example, the left-hand side that it's shifting towards only has the 1 mole of gas species. Conversely here, if we decreased the pressure, I'll do this one in green, that's going to favor the side with more moles. So that will shift in this direction. And I would see that this equilibrium here would shift back. And again, how far it shifts and how much that changes depends on many other factors, but it will shift the equilibrium to the right. New rate of reaction established, equal forward and backwards. New concentrations, Kc unchanged. So really you have to look carefully at those subscripts when dealing with pressure because it only affects gas molecules. And when you're writing out an explanation for this, you have to indicate that it's the gas number of molecules or moles rather that you're looking at. So you have to include that language in your answer. Gas moles, gaseous moles, gas substances, anything that indicates that you understand that the pressure is only affecting the gases is of the utmost importance. One last example to look at. Let's say the equilibrium is going to be over here this time. Change it up a bit. Here we look and we see, okay, well, I see a solid and I see 3 moles of gas, and now I see 3 moles of gas, so they're equal. So what that means here is if I have a pressure and I can increase it, well, it's going to favor the side with less gas moles. But they both have 3 gas moles. So that means the equilibrium will be unchanged. Same if I decrease it. Again, it's going to favor the side with more gas moles, but they both have 3. So the equilibrium here will be unchanged in this scenario. Equilibrium unchanged. This is also true if I had no gas species at all. And we were asking about changes in pressure. It's kind of a trick question. There's no gas moles, so there's no change in equilibrium with that. So watch for that. Either equal number of gas moles on both sides or no gas species at all present in the reaction. Changes of pressure will have no effect. And again, Kc doesn't change because the only thing that will change Kc is temperature. Thank you very much for watching this. I hope it's been helpful, and thank you very much for listening.